Welcome to Networks Professionals.
Welcome to The Explainer. Today, we're untangling a seriously foundational part of network traffic management, collision and broadcast domains. We're going to look at exactly how data moves effectively and, honestly, more importantly, why it sometimes just doesn't.
You know the feeling. We've all seen networks suddenly slow to a crawl or randomly drop data. But bad internet is rarely the actual diagnosis, right? Unmanaged networks suffer from very real physical and logical traffic jams. So today, we're going to examine the underlying structural bottlenecks causing all this chaos and figure out how to actually engineer our way out of them. Here's our quick agenda for today. First, the network traffic problem. Then, inside the collision domain, followed by inside the broadcast domain. After that, we'll compare collisions versus broadcasts and wrap up with optimizing network efficiency. Let's dive in. Starting off with Section 1, the network traffic problem. When your unmanaged networks are facing severe data loss and massive congestion, it's pretty much never just a random glitch. It's almost always a deep architectural issue. See, if your domains aren't segmented properly, both physically and logically, the whole environment just gets completely saturated. And that resulting noise, it degrades the entire system, leading to dropped packets and, frankly, unacceptable latency. Moving right along to Section 2, inside the collision domain. Okay, so what exactly is a collision domain? Well, it's basically a network segment where simultaneous transmissions from devices literally clash, which just destroys the data. Picture a totally chaotic four-way intersection with absolutely no stoplights. When two devices try to talk at the exact same time, especially on a half-duplex link, their signals physically collide right there on the wire. The voltage spikes and the data is completely ruined. These physical crashes happen right down at layer 1, the physical layer. You'll see this all the time in older setups using hubs or repeaters, mainly because a hub just blindly forwards incoming data out of every single other port. When a collision happens, the network has to rely on mechanisms like CSMA/CD, that's Carrier Sense Multiple Access with Collision Detection. Basically, both devices have to back off, wait a random amount of time, and then try to retransmit. As you can imagine, this constant back and forth completely tanks your network performance. All right, Section 3, inside the broadcast domain. Now, a broadcast domain is the area where a broadcast message sent by one device is received by literally every other device on that network. Think of it like this. If a collision domain is a car crash, a broadcast domain is like a really loud PA system in a giant office building. Everyone is forced to drop whatever they're doing, process the header, and check if the message is actually for them. Since these operate a bit higher up at the data link and network layers, your standard Layer 2 switches and hubs are going to combine all their ports into one giant broadcast domain by default. And if you have too many devices sending out ARP requests or system broadcasts, boom, logical congestion. The CPU cycles of every single device are just wasted processing entirely irrelevant frames. The only way to stop that pace system from reaching everyone is by bringing in a router or a Layer 3 switch to act as a hard boundary and block those broadcasts from spreading. Let's move to Section 4, collisions versus broadcasts. Let's put these two head-to-head because the distinction is absolutely crucial. Collision domains deal strictly with physical data clashes. We're talking electrical or optical signals literally overlapping on the transmission medium. Broadcast domains, on the other hand, are all about logical traffic distribution. So one is a physical traffic jam that requires annoying retransmissions. The other is a logical scaling issue where every single node is forced to receive and process traffic it doesn't even care about. Structurally, this is kind of wild. They work a bit like Russian nesting dolls. There's a very distinct hierarchy in network design. Because routers stop broadcasts, but standard switches only stop collisions, you typically end up with one large logical broadcast domain that actually contains several smaller, localized physical collision domains nested right inside of it. Which brings us to our final part, Section 5, optimizing network efficiency. At the end of the day, managing all this traffic really comes down to your hardware. Hubs and repeaters, they are the absolute worst offenders here, creating massive, sprawling domains for both collisions and broadcasts. But then, switches step in and actively segment those collision domains, essentially giving every single port its own safe lane. And finally, routers and Layer 3 switches step up to physically break apart those massive broadcast domains. But here is a super crucial architectural nuance you gotta remember. While switches divide collision domains per port, which is great, it basically eliminates those physical crashes by giving everyone dedicated bandwidth, they still share a single broadcast domain by default. So a switch fixes the crazy intersection, but it absolutely does not silence that building-wide PA system.
So it really all boils down to this fundamental principle. Reducing collision domains improves your transmission efficiency by freeing up the physical wire itself, while reducing broadcast domains improves network chatter and logical congestion by strictly limiting who actually hears the noise. Basically, segment with switches for hardware efficiency and segment with routers for a quiet, highly optimized network. So here's my question for you. Are you effectively reducing chatter and actually improving efficiency in your own systems? Next time you're looking at a network topology, I want you to try and spot the physical clash zones and the logical congestion zones. It's like a giant puzzle once you know what to look for. Thanks so much for joining me for this explainer, and I will see you next time.
Thanks for watching.